We have only 3 more days until spring break. Remember that this Friday is a school holiday to celebrate Cesar Chavez Day. Okay, so before we start, should we review quiz 8? No? Yes. Okay, so the structure of glycine, the simplest amino acid, is shown on this slide. So which protons are acidic in glycine? So it's the one on the acid function group, which is this one, and there's also one of the protons of these 3 on the amine functional group. And then which one is the strongest acid? Is it going to be this proton or that proton? Yeah, so why is it this one? Yes, note that the lower the pKa, the stronger the acid. Part B, draw a titration curve for glycine. So for glycine, there's 2 protons which are donated, so that means that there's going to be two endpoints. Okay, so it's going to look something like this. And then you want to also label a pH at the starting point, each halfway point, each endpoint. So we're going to do it. Let's see, we have 1, 2, 3. We have 5 points. To associate a pH with. So at the first halfway point, that's equal to pKa, so that's going to be 2.34. At the second halfway point, the pH equals pKa2, which is 9.60. At the first endpoint, the pH is equal to 1/2 pKa1 plus pKa2. So let's see, we add these 2 up, divided by 2. So let's see, that's 11.94 divided by 2. So that's 5.97. Now we've got to do a calculation to figure out the pH at the starting point. So we want to use Ka1 here. So for this one, let's see, we want to use the formula, let's see, we'll call it H2A, going H plus HA minus. And then we do our equilibrium calculation. So this is the initial amount, the amount of reacts. We can assume that the concentration of H2A or glycine is 0.1 molar. So, is this getting mechanical for you, where you can just do it without thinking about it anymore? Okay, so then you solve for, let's see, so then you have a 10 to the minus 2.34 power, which is the Ka, and that's equal to x times x divided by 0.1 minus x. And then we do our usual assumption here. So if we solve for x, if we solve for x, x is equal to well, I didn't do the calculation, but anyway, the pH at the starting point is 1.67. At the second endpoint, we want to use Kb, so for that one, we have A2 minus reacting with water, forming HA minus plus OH minus. This is going to be KB. So when we do this calculation, this is equal to 1 times 10 minus 14 divided by, let's see, 10 to the minus 9.6 power. And then we do our equilibrium calculation again. So from here, we need to know the initial concentration A minus, so it's going to be 0.1 molar here. No. So if we start with 20 milliliters of the glycine at the first endpoint, we're going to need how many milliliters of base? Yes, we need 20 here. And to get to the second endpoint, yeah, we need a total of 40 milliliters of base. So note that if we have 20 plus 40, that's equal to 60 milliliters of solution. So if we use our dilution equation, we have C original times V original equals C dilute times V dilute. So if we have 0.1 times something, so what goes in this box here? What goes in this one? X. What goes in VD? Yeah, 60. So if we solve for CD, that's equal to, yeah, so 20 divided by 60 is 1/3, so 0.1 divided by 3 is 0.033 molar. So that's going to be our initial amount. Okay, so if we solve for X, this gives us the hydroxide ion concentration. And from here, we can calculate the POH. And then from pH, we can calculate from POH, we can calculate the pH. And when you do this calculation, let's see, I got for the pH 11.1. So for this one up here, it's 11.1. This is 11.1. Part C, what is the isoelectric point of glycine? So this is the fully protonated form of glycine. And what is the charge of glycine in that structure? Yes, that's +1. So the +1 charge is going to be here at the starting point. At the halfway point, what's going to be the charge on glycine? Yeah, +1 and 0. So at this point here, it should be 0. And then here it's going to be 0 and -1. And finally, at the second endpoint, the structure is going to be, the charge is going to be -1. So that means that the isoelectric point of glycine is boy, we're all ready for spring break. So how many of you guys are going down to, whether you go to Florida or Palm Springs? Or, could glycine be used for a pH 5 buffer? So note that these regions where the pH is relatively flat these are the buffer regions. And then we said that for a buffer, it's got to be the buffer pH has got to be near the pKa. So we said it was a pKa plus or minus 2. So if we look at this one, plus or minus 2 from this is from 0.34 to 4.34. And for this one, it's going to be 7.6 to 11.6. So pH 5 doesn't fall within that range. So pH 5 is somewhere here, which is outside that buffer region. So I'm sure this is probably not as exciting as watching young children fight to the death in the Hunger Games, but no, again, it's still a picture. Anyone watch that movie? Watch the kids kill each other?
Overrated. Did you watch that?
Did you watch it, Mr.?
I haven't seen a movie in years. I just watch the trailers because the best part's on the trailer anyway.
That is true.
I figure if I watch 3 minutes of the trailer, I don't have to spend $12 to watch the movie. Whatever it costs.
Yeah, what was the last movie you watched?
The Seeds movie.
Yeah, the Seeds movie.
Was there supposed to be an earthquake or something in the movie?
Yeah, you wouldn't know.
Earthquake or elephants walking along running along the bush or something?
No, I'm saying in the theater they have movies.
What was the last movie you watched?
I watched Karate Kid 2.
Like that one?
See the original, if you guys watched the original Karate Kid, that was good too. Okay, so let's talk about blood buffers. Now there's two blood buffer systems in our blood. One is baking soda, the other one is hemoglobin. So we're going to look at the baking soda blood buffer system in our blood. So we know that a buffer is effective only in the region of its pKa. Blood has a normal pH of about 7.4, and it's important that the blood remain constant because if the pH of our blood goes below 6.8 or rises above 8.0, our cells can't function properly and death may result. So it says here that the bicarbonate CO2 blood buffer in vivo is an open system in which the concentration of dissolved CO2 is maintained constant. Okay, so any excess CO2 is produced by this reaction. So we have H+, H plus represents the proton plus the bicarbonate ion. That goes to H2O and CO2. Now, we've seen the reverse of, let's see, now we've seen this reaction in Chem1A when we were looking at gas-forming reactions. Anyway, CO2 is expelled by any excess CO2 is expelled by the lungs. Note that a typical lab buffer is a closed system. So the concentration of the conjugate acid increases when H plus reacts with the conjugate base. So in this HCO3 minus CO2 blood buffer, which substance of these two is the acid and which one is the base?
CO2 is the acid.
Okay, so what do you guys think about that for a minute? Okay, so which one is the acid, which one is the base? Okay, so what we've talked about so far is we know that, for example, HCO3 minus, is this substance an acid or a base? It could be a base. So, for example, if it's a base, it can accept a proton, and it can form the acid H2CO3, but the HCO3 minus can behave like an acid. Yeah, it forms H plus and CO3 2 minus. So note that HCO3 minus can behave like either an acid or a base. So in the blood buffer system, does it behave like an acid or a base? So who says that the HCO3 minus behaves like an acid in this blood buffer system? No, but in this system. I mean, yeah, it can, but doesn't in the blood buffer system.
Does it not behave as cold? Depending on what the body
No, in this system.
If it needs to be more acidic or it needs to be more basic.
No, but see in the range of the pH, around 7.4. Does it behave like an acid or a base? Who says it behaves like an acid? Oh, so therefore you guys are right because you're right. Since none of you are raising your hand for an acid, therefore you're saying it's a base when you're right. So that means that the CO2 behaves like the acid. Now note that CO2 isn't a typical acid because are there any protons in CO2? No. So what happens is that the CO2 reacts with the